Hey there, and welcome. If you're trying to cut through all the confusing tech jargon out there and, actually figure out what all those letters mean, you're definitely in the right place.
Yeah, this is Acronym Academy. We're your shortcut for making sense of those complex technical topics, especially when it comes to networking.
Absolutely. And today, we are diving headfirst into what can feel like a real alphabet soup. Networking acronyms.
Oh, yeah.
Seriously, if you're studying for something like the CCNA, or maybe you just work in IT, these terms just fly at you constantly.
They really do. And mastering them isn't just about, passing a test. It's really about speaking the language of networks, feeling confident.
Exactly. Knowing what's actually going on.
Right. And there are so many. It can feel a bit like hitting a wall of letters sometimes.
Yeah.
So our mission today is pretty simple. Break down the really essential ones you're going to see.
The ones you'll use day to day or definitely see on the exam.
Yeah, the foundational ones. We want to help turn that potential confusion into real clarity.
Okay, so here's the plan. We've gathered some key terms, and we're going to group them logically, try to make sense of them together.
And for each one, we'll spell it out, obviously, explain what it actually means.
And maybe throw in a helpful analogy if we can, and then talk about where you'd actually see it, in the real world or on that exam.
Sounds good. Let's start right at the beginning then with the fundamental concepts and models, the frameworks we use to think about networks.
Okay, kicking us off. The big one, the conceptual model. OSI.
Right, OSI. That stands for Open Systems Interconnection.
Okay.
It's a conceptual model. So think of it like a universal blueprint, maybe. It standardizes all the different jobs a network system has to do into 7 distinct layers.
7 layers, okay. Like from the physical wires all the way up to the software you're using.
Exactly. Layer 1, the physical stuff, up to layer 7, the application layer. It helps break down this really complex thing, networking, into smaller, more manageable pieces.
Right, like building something complex layer by layer, following instructions, not just looking at a giant blob.
Precisely. And the real power comes in troubleshooting. If you know, say, your problem is at layer 2, not layer 7.
It tells you where to look.
Exactly. It narrows down the possibilities hugely. You know which tools to use, what things to check.
Okay, so OSI is the big conceptual framework. But the model we actually use day-to-day on the internet, that's TCP/IP, right?
That's the one. TCP/IP Transmission Control Protocol Internet Protocol. This is the protocol suite, the set of rules that basically powers the internet and, well, most modern networks.
So it's the practical working model, not just the blueprint.
Yeah, you could say that. If OSI is the detailed 7-layer recipe,
TCP/IP is the slightly simpler, maybe 4-layer cake we actually bake and eat.
I like that. Yeah, it covers similar functions, but it's structured a bit differently, more practically. Think of it like the whole postal service system.
Okay.
It's got the rules for addressing the envelope, that's the IP part, and rules for how the package itself is handled, making sure it gets there reliably, that's TCP, or sometimes UDP.
Gotcha. So let's break that down then. The addressing part first, IP.
IP Internet Protocol. This is fundamental. It's the main protocol for putting addresses on data packets and then routing them across networks so they reach the right destination device.
So IP is literally the address, like the street address and zip code on that package.
Exactly that. It tells the network where the data needs to go. Every single device connected to an IP network needs an IP address to communicate.
And we hear about different versions, right?
We do. You'll constantly work with IPv4. That's the older one we still mostly use.
The number is like 192.168.1.1.
Yeah, those dotted decimals. But we've largely run out of those. So the future, and increasingly the present, is IPv6. Much, much larger address space. Looks quite different.
Okay, so IP handles the where. What about how the data gets there? You mentioned TCP handles the reliability part.
Right. So TCP Transmission Control Protocol. This one's crucial. It's connection-oriented, meaning it sets up a connection before sending any data. Like a phone call, you establish the connection first. And it's reliable. It uses things like sequence numbers, acknowledgements.
So it checks if the data arrived.
Yes, and if it arrived in the right order, and if any pieces are missing, it asks for them again. It guarantees delivery.
Like sending a registered letter. You need that signature, confirmation it was received, and that it's all there.
Perfect analogy. Because of that guarantee, TCP is used for things where accuracy is paramount. Like loading a web page with HTTP, you need all the pieces.
Or sending an email, or transferring a file with FTP. Makes sense.
Exactly.
But what if speed is more important? Like maybe losing a tiny bit of data is okay if the rest gets there faster.
Then you're probably looking at UDP. UDP, User Datagram Protocol.
Okay.
It's the opposite of TCP in many ways. It's connectionless, no setup required, just sends, and it's unreliable.
Unreliable. That sounds bad.
Well, it just means it doesn't have those built-in checks and guarantees like TCP. It sends the data, but doesn't confirm delivery or order.
Ah, the postcard. You mentioned that before. Drop it in the mail, it's fast, but maybe it gets lost, maybe others arrive first. You don't get confirmation.
Exactly. That speed makes it great for things like streaming video, VOD or live streams or online gaming or voice over IP calls or IP.
Right, because if one tiny packet drops in a video stream, you might see a tiny glitch, but you don't want the whole thing to stop and wait for a resend.
Precisely. Speed over perfect reliability in those cases.
Okay. Now, when we're sending these packets, TCP or UDP, is there a size limit? Can they be too big?
Yes, there is. It's called the MTU, Maximum Transmission Unit.
Maximum Transmission Unit.
It's the largest size, in bytes, that a single data packet can be without needing to be broken up or fragmented as it travels across a specific network link.
Like the maximum size box you can fit on a conveyor belt. If it's too big, you have to unpack it and put it in smaller boxes.
That's a great way to think about it. Different network types, like Ethernet versus maybe a DSL link, can have different MTUs. If a packet hits a link with a smaller MTU, it has to be fragmented.
And that adds overhead. Slows things down.
It can, yeah. That's complexity. So understanding MTU is important for network performance, especially when you're troubleshooting weird connectivity issues across different network paths.
Okay. And what stops a packet just bouncing around the internet forever if, say, there's a routing mistake and it can't find its destination?
Ah, good question.
Yeah.
That's the job of TTL. TTL, time to live.
Time to live sounds dramatic.
It's actually a value, a number inside the IP packet header. Every time that packet passes through a router that's called a hop,
Right.
the router decreases the TTL value by 1. If that TTL value ever hits 0.
The router just drops it, throws it away.
Exactly. Discards the packet. This is crucial to prevent packets caught in routing loops from circulating endlessly and clogging up the network.
Like an expiration date stamped on the package.
Yeah,
Counts down the number of stops it can make.
precisely. You'll actually see TTL values when you use tools like ping or traceroute. It helps diagnose loops or just see how many hops away a destination is.
Okay, let's zoom in a bit. Down to the local level. Every network card, every Wi-Fi adapter, they have unique number burned into them, right?
Yeah.
Not the IP address, something else.
You're talking about the MAC address. MAC, Media Access Control.
ED access control.
Yes. It's a unique physical identifier assigned to a network interface card, or NIC. It operates at layer 2 of the OSI model, the data link layer,
So the IP address is like the temporary street address where the device is right now on the network.
which can change, yeah.
But the MC address is like the device's unique serial number, permanently etched on it.
Exactly. It doesn't change just because you move the device to a different network. Switches use these MC addresses to forward data frames locally within the same network segment, or LAN.
LAN, local area network, we'll come back to that.
Right. And interestingly, the first half of a MAC address is called the OUI,
OUI.
Organizationally Unique Identifier. It actually tells you which company manufactured that network card. Cisco has its own OUIs, Intel has theirs, and so on.
Huh, neat. Okay, that covers some really fundamental stuff models, addressing basic protocols. Let's shift gears maybe to the services and protocols that run on top of this foundation, the things that make the internet actually useful day to day.
Sure. We already mentioned HTTP briefly, HTTP Hypertext Transfer Protocol.
Right, that's what my browser uses to grab web pages.
That's the one. It's the protocol for transferring data, mostly websites, across the www, the World Wide Web. You see HTTPS now mostly, the secure version.
Gotcha. And, okay, magic question. How does my phone or my laptop automatically get an IP address and all the right settings when I join my home Wi-Fi or the coffee shop network? I don't type any of that stuff in.
That's the magic of DHCP. DHCP, Dynamic Host Configuration Protocol.
Dynamic Host Configuration Protocol.
It's a network management protocol, usually a server running on the network whose job is to automatically assign IP addresses
Okay.
and other critical info like the subnet mask, the default gateway router address, and importantly, the DNS server addresses to devices when they join the network.
Like the front desk at a hotel. You check in, they automatically give you a room number, tell you how to get to the elevator, maybe give you the Wi-Fi code.
Exactly. It makes managing networks vastly simpler. Imagine having to manually configure every single device. And it's seamless for users.
Yeah, thank goodness for DHCP. Now, you mentioned DNS there. how does my computer know that Acronym.Academy actually means, some specific IP address somewhere?
Ah, yes, DNS. DNS, Domain Name Service, or system. This is absolutely critical. Think of it as the internet's phone book.
The phone book, okay.
A name like Google.com or Acronym.Academy, but computers need the number, the IP address, to actually connect. DNS does that translation.
So I type the name, my computer asks the DNS server, hey, what's the number for this name? And DNS gives back the IP address.
Precisely. It's a huge, hierarchical, distributed database system that maps those human-friendly names to the numerical IP addresses. It happens constantly behind the scenes every time you browse the web or access network resources by name.
Wow. Okay, wouldn't work without it. What about when things go wrong? Like, if I try to ping a server and it's down, how does my computer know it's unreachable?
Network devices use ICMP for that. ICMP, Internet Control Message Protocol.
Internet Control Message Protocol.
Its main job is sending error messages and operational information about the network itself. It works at the network layer alongside IP.
So it's like the network's own messaging system for problems, like getting a delivery failed notice from the postal service.
That's a good way to think about it. When you use the ping command, you're sending ICMP echo request messages and hoping to get ICMP echo reply messages back. If you get a destination unreachable message, that's ICMP telling you there's a problem somewhere along the path. Traceroute also relies heavily on ICMP to map the path packets take.
Okay, that makes sense. So foundational models, core services, how does data actually get between different networks across the internet? That's routing, right?
Exactly, routing. And routers need rules, protocols to figure out the best path. Let's start with an older, simpler one, RIP.
RIP, Routing Information Protocol. Doesn't sound too lively.
Well, it's a distance vector protocol. Its main way of deciding the best path is just by hop count.
Hop count? You mean the number of routers it has to go through?
Yeah. It basically asks its neighbors how many hops away is network X, and it chooses the path with the fewest hops.
Like asking directions by counting the number of houses you pass.
Kind of. It's simple, which is good for small, uncomplicated networks. But just counting hops isn't always best. A path with fewer hops might actually be much slower if the links are low bandwidth.
Right, doesn't consider link speed or anything, so that's common now.
Much less common in larger networks, yeah. Which leads us to something more advanced, especially in Cisco environments, EIGRP.
EIGRP, Enhanced Interior Gateway Routing Protocol. Okay, enhanced sounds better.
It is. It's a Cisco proprietary protocol, though parts have been opened up. It's a hybrid protocol, sometimes called Advanced Distance Vector. Crucially, it doesn't just use hop count.
What does it use?
It calculates a metric based on several factors: bandwidth, delay, load, reliability, to get a much better picture of the actual best path.
Smarter. And it's known for converging quickly, right? Like adapting fast if something changes.
Yes, very fast convergence. It uses a special algorithm called DUAL, the diffusing update algorithm. It helps prevent loops and allows routers to quickly find backup paths if a primary path goes down. Very efficient, especially in all Cisco networks.
Okay, now what about a non-proprietary, widely used advanced protocol? I hear OSPF a lot.
You do, OSPF, Open Shortest Path First. This is a link state protocol, which is fundamentally different from distance vector like RIP.
In state, how's that different?
Instead of just telling neighbors network X is 5 hops away, each OSPF router describes its own connections, its links, their state up, down, and their cost or metric.
So it's like each router shares its own little piece of the local map.
Exactly. It floods these descriptions, called LSAs, link state advertisements, throughout its area. Every router in the area collects all these LSAs.
And builds a complete picture.
Precisely. Each router independently builds an identical, complete map, a topology database of the network area based on all the LSAs it received.
Okay, so everyone has the full map.
And then each router runs the SPF algorithm shortest path first on that map to calculate the absolute best loop-free path to every destination from its own perspective.
Wow, okay. That sounds robust. Makes sense why it's used in larger, complex enterprise networks.
It's very scalable and stable, yes. Divides networks into areas to manage complexity.
All right, so we have RIP, EIGRP, OSPF for routing within a single organization's network generally. What about routing between totally separate networks, like across the actual internet?
Now you're talking about the big one, BGP. BGP, Border Gateway Protocol.
Border Gateway Protocol.
This is the protocol of the internet. It's an exterior gateway protocol used to exchange routing information between different autonomous systems, or ACE.
Autonomous systems. ACEs, what are those?
Think of an AS as a large network or a collection of networks under a single administrative control, like your ISP or Google's network or a university's network. Each one is an AS.
Okay, so BGP is how, say, Comcast talks to Verizon, or how my company network talks to its internet provider to figure out how to reach addresses on each other's networks.
Exactly. It's how routing information propagates across the entire globe. It's less about finding the shortest path technically and much more about policy.
Policy, like business agreement.
Yes, which paths are preferred, which peer networks to use, costs, politics. It all plays into BGP routing decisions between ACEs. It's like the negotiations between different countries on how to route international flights.
Fascinating. So it literally holds the internet together.
Pretty much. You'll hear about eBGP, external BGP, which runs between different ACEs, and iBGP, internal BGP, which is used to carry that external routing information within a single AS.
Okay, wow. We've covered quite a bit already. From the basic models like OSI and TCP/IP, how data gets addressed and sent reliably or quickly, the services like DNS and DHCP that make things work, and now how data finds its way across networks big and small using routing.
Yeah, it's definitely a journey through the layers and protocols, but hopefully seeing how they connect, how TCP and UDP rely on IP, how routing directs IP packets, helps it all make a bit more sense.
It does. And hey, for everyone listening, how are you doing with all this? Taking notes. If you're finding this deep dive helpful in untangling these acronyms, maybe take like half a second right now to hit that like button.
Yeah, and subscribe to Acronym Academy if you haven't already. We try to make this stuff easier to digest.
Definitely subscribe. And share this with anyone else you know who's wrestling with networking. Oh, and leave us a comment below. Let us know maybe which acronym here is your favorite, or perhaps one that still trips you up. We actually love hearing from you.
We do. Okay, ready to keep going. Let's pivot a bit toward switching concepts, security, and some other key terms.
Sounds good. Let's talk about organizing things on a local switch. VLANs.
Right, VLAN, virtual LAN. This is a really powerful concept. It lets you take a single physical switch and logically divide it up into multiple separate broadcast domains.
Okay, so instead of needing, say, 3 physical switches to keep accounting, sales, and engineering networks separate,
you could potentially use one larger switch and create 3 VLANs. Devices in one VLAN can't directly talk to devices in another VLAN, even if they're plugged into the same physical switch, unless you specifically allow it with routing.
like putting up virtual walls inside a big open office. Creates separate rooms even though it's all one floor.
That's a perfect analogy. It's huge for security, for managing traffic, for performance, keeping broadcast traffic contained within each VLAN.
Makes sense. You separate different departments, or maybe separate voice traffic from data traffic.
Exactly.
Yeah.
And you might hear related terms like VTP VLAN trunking protocol, which is a Cisco way to manage VLANs across multiple switches, or SVI, switched virtual interface. Yeah, that's like a virtual router interface on the switch itself that allows you to route traffic between different VLANs if you need to.
Okay. Now, switches often have redundant links between them for backup, right? But doesn't that create loops? I thought loops were bad.
Loops are very bad in Ethernet. They can cause broadcast storms that melt down your network. That's why we have SDP.
STP, spanning tree protocol.
Exactly. Its entire job is to prevent these layer 2 loops when you have redundant paths.
How does it do that?
It uses an algorithm, the STA, spanning tree algorithm, to figure out the network topology. If it detects a potential loop, basically, more than one active path between any 2 switches, it intelligently blocks one of the redundant paths.
Blocks it, like shuts down the port.
Temporarily puts the port into a blocking state for normal data traffic. It keeps the physical redundancy for failover, but ensures only one path is active at any given time, preventing loops.
Like a traffic manager closing one of 2 parallel roads to prevent jams, but ready to reopen it if the main road gets blocked.
Precisely. Essential for stable switch networks with redundant links.
Okay. Now, something Cisco specific. How do I quickly find out what's plugged into the other end of a cable connected to my Cisco switcher router?
You'd use CDP, Cisco Discovery Protocol.
Cisco Discovery Protocol.
It's proprietary to Cisco. Devices running CDP periodically send out messages announcing themselves to their directly connected neighbors.
So my Cisco switch can tell me, hey, the device plugged into port 5 is another Cisco switch named Core SW1 running this iOS version, and it's connected to its port Gigabit Ethernet 01.
Exactly that level of detail. Host name, platform, capabilities, the specific ports involved. It's incredibly useful for network engineers to quickly map out connections and verify physical cabling without needing IP addresses yet.
Very handy. Okay, shifting to security a bit. How do we control what traffic is allowed or denied through a router interface, for example?
That's the job of ACLs.
ACL, access control lists.
Access control lists. An ACL is basically a list of rules permit or deny statements that you apply to an interface. The router then examines packets passing through that interface against the list rule by rule.
Like a security guard at a door with a very specific list.
Yeah.
Okay, you match rule #1, you're denied. You match rule #2, you're permitted.
Exactly. The rules specify criteria like the source IP address, destination IP address, protocol type, TCP, UDP, ICMP, and even specific port numbers.
So you could say, allow web traffic, HTTP, HTTPS, from the internal network to the internet, but deny everything else.
Precisely. Or deny traffic from the specific server trying to reach the finance department's network. Very powerful for filtering traffic and implementing security policies. You'll see them on routers called RACLs, and sometimes even applied to VLANs on switches called VACLs.
Yes. Okay, another really common one, especially for home users connecting to the internet, NAT. And maybe PAT.
Yes, NAT, network address translation, and its most common form, PAT, port address translation.
Okay, what's the difference?
NAT, broadly, is the process of modifying IP address information in packet headers as they cross a router. Usually, it translates private internal IP addresses, like 192.168.x.x in your home, into a public internet routable IP address, the one your ISP gives you.
Why do we need to do that?
Because there aren't enough public IPv4 addresses for every device, so we use private addresses internally. NAT lets many devices using private IPs share one single public IP to get out to the internet.
Ah, okay. So where does PAT come in?
PAT is the specific type of NAT almost everyone uses. It takes multiple private IPs and maps them all to the same single public IP address, but assigns a different source port number for each outgoing connection.
Port number.
Yeah, like TCP or UDP port numbers. So when return traffic comes back from the internet to that single public IP, the router looks at the destination port number on the packet and knows which internal private IP device the traffic belongs to.
So NAT is the general idea of changing addresses. PAT is the trick of using port numbers so many private devices can share one public IP.
Exactly. It's sometimes called NAT overload.
Like the post office changing the return address to the main branch, but PAT adds a unique box number for each person sending mail, so replies get routed correctly.
That's a pretty good analogy. It's fundamental to how home and small business networks connect to the internet today with IPv4.
Cool. What about connecting securely over the internet? Like working from home and accessing company servers.
For that, you'd use a VPN. VPN, Virtual Private Network.
Virtual Private Network.
A VPN creates a secure, encrypted connection, often called a tunnel, over a less secure network, typically the public internet.
So it's like building your own private, secure tunnel inside the public highway system. Data traveling inside the tunnel is hidden and protected.
That's the core idea. It makes it seem like your remote computer is directly connected to the private company network. Securely.
Essential for remote work, or even just for privacy when using public Wi-Fi.
Absolutely. And a common set of protocols used to build and secure these VPN tunnels is IPsec. IPsec, IP security.
IPsec. Good to know. Okay, just a few more foundational terms we probably should cover. We mentioned iOS earlier with CDP.
Right, iOS, Internet Working Operating System. This is the software, the operating system that runs on most Cisco routers and switches.
So when you're typing commands into that black screen with white text.
The CLI, Command Line Interface. Yep, you're interacting with Cisco iOS or one of its variants like iOS XE, iOS XR, depending on the device. It's where network engineers spend a lot of their time configuring things.
Got it. And we mentioned LAN.
LAN, Local Area Network. Pretty straightforward. It's a network contained within a small physical area. Your home network is a LAN. An office building network is typically a LAN. Devices usually connect via Ethernet cables or local Wi-Fi.
And when you connect multiple LANs together, maybe across different cities.
Then you have a WAN, WAN, Wide Area Network. This spans a larger geographical area, connecting LANs that might be miles or even continents apart. Technologies like MPLS, leased lines, or even the internet itself are used to build WANs.
The internet being the biggest WAN of all.
Pretty much.
Okay, last one. A general term for the chunks of data at different network layers.
Ah, yes. The PDU, Protocol Data Unit.
Protocol Data Unit.
It's just the generic term for a unit of data at any given layer of a networking model like OSI or TCP/IP. But the key thing is we call it different names at different layers, which can be confusing.
Okay. Like what?
At the transport layer, layer 4, the PDU is called a segment if it's TCP, or a datagram if it's UDP. At the network layer, layer 3, the PDU carrying the IP address information is called a packet.
Segment, datagram, packet.
Okay. Then, down at the data link layer, layer 2, where the MMAS addresses live, the PDU is called a frame. And finally, at the physical layer, layer 1, we're just talking about bits.
Segment, packet, frame, bits. Wow. So PDU is the umbrella term, but the specific name tells you which layer you're talking about.
Exactly. It helps technical conversations be more precise about where in the communication process something is happening.
Got it. Wow. Okay. I think that covers the main list we set out to tackle.
Yeah.
That was a lot of acronyms.
It really was. OSI, TCP/IP, IP, TCP, UDP, MTU, TTL, MAC, OUI, HTTP, WWW, DHCP, DNS, ICMP, RIP, EIGRP, Dual, OSPF, LSA, SPF, BGP, ABGP, IBGP, VLAN, VTP, SVI, STP, CDP, ACL, RACL, VACL, NAT, PAT, VPN, IPsec, IOS, CLI, LAN, WAN, PDU, segment, packet, frame, bits. Yeah, deep breath.
Seriously. And look, if your head is spinning a little bit right now listening to this, that is completely okay. It's totally normal. Networking really does have its own language.
It does. And mastering it just takes time, exposure, practice. The more you encounter these terms, use them, hear them in context, the more they start to stick and become second nature.
Definitely don't feel like you need to have memorized everything perfectly from just this one deep dive.
No way. Think of this as maybe a helpful reference you can come back to. Getting comfortable with these terms truly is the key to unlocking so much understanding in IT and networking. It builds the foundation.
It really does. Well, a huge heartfelt thank you from both of us for joining us on this expedition through the networking acronym jungle today. We genuinely hope it helped clear things up a bit for you.
Yeah, we really do. And if you did find it valuable, if it helped connect some dots, please do hit that like button down below. It helps others find this too.
And share it. Share it with a friend, a colleague, anyone you know who's maybe studying for their CCNA or just trying to get a better handle on networking concepts.
And absolutely, please subscribe to Acronym Academy. We're going to keep trying to break down these complex tech topics into more understandable chunks.
Yes, subscribe. We're here for you, making tech less intimidating, one bite-sized deep dive at a time. Your support really does help us keep creating this content.
And stay tuned for more shortcuts to knowledge right here.
So, just to leave you with a final thought to chew on. We've talked about all these acronyms as the fundamental building blocks of today's networks. As technology keeps racing forward, new protocols, new ideas emerge. How does really understanding these core terms, not just memorizing them, prepare us to adapt and grasp the networking challenges and innovations of tomorrow?
That's a good question. Something to think about as you continue on your learning path.
Definitely. Thanks again for diving deep with us. We'll catch you on the next one.